Yeah, thanks for the introduction. Yeah, today I'll talk about this paper called AlgoTune that was published in NeRPS of last year. Um, and yes, as mentioned, I am an ML researcher at Nebius, and I previously did my PhD at the University of Tübingen with Matthias Bethke. So I want to quickly just talk about my ideal benchmark, and it basically has two things that make it really good. One is it's very challenging. So as we know, benchmarks get released, and then very quickly, models get to very high accuracies on those benchmarks. And so I want my ideal benchmark to be very hard, even for good models, preferably for as long as possible. I want it to be very, very hard. And the second thing is I want it to be realistic. I want my ideal benchmark to be very connected to a real world task. Like if you make progress on this benchmark, then I want this to be very easy to translate to real world value. And then as a bonus, I want my benchmark not to be in the training data, or maybe if that's too hard, I want the fact that my benchmark exists in the training data not to help you out in any way. And this might sound pretty hard to achieve, but I want to introduce you to AlgoTune, which I think does all three of these. So in AlgoTune, we take a bunch of very popular and widely used functions from NumPy, from Python libraries. So like NumPy, like SciPy, or Python's own functions like gzip. And the goal, so you're given one of these functions, and the goal is to optimize the runtime of that function. Yeah, so we basically have a reference function, which in this case is maybe like this NumPy QR function. And I'm going to ask the LLM to generate its own version of that function. And I'm going to give it the same hardware. I'm going to give both functions the same hardware. And I'm going to tell the LLM, look, you have this time limit, however long it took NumPy QR to run. And you got to give me a reference implementation that runs quicker than it. Okay, just improve the runtime. Yeah, and of course, your function that you give me not only has to be faster, but it has to be to have the same or roughly the same outputs as the original function. You can't just make something completely new. Okay, so basically, I'm going to have these tasks. Each task will have a function, and I'm going to quickly describe how we built this benchmark. So for each one of these tasks, we need the following. We need a reference function, of course. So it could be like a gzip or QR or some SciPy function. We need some input data, right? This will be used to compare the reference function and the LLM generated function. And we need a solution verifier. So we need a function that tells us if your given solution is both optimal and valid. So you can think about a problem like traveling salesman, where a solution, there are many, many solutions. And so instead of just having a list of possible solutions, we just have a function that checks that your solution is both valid and optimal. So an example task might look like this. We have this function called generate problem that is going to generate a bunch of inputs for us. So it takes just a random seed and a variable n, which is tied to the difficulty of the problem. And so for PCA, we have this pretty simple function that just generates some random matrix. And then we're going to have a solver function. This is a reference function. So for PCA, we used sklearn's PCA implementation. This is the function that we're going to have to try to beat in runtime. And we're going to have our solution verifier called isSolution that will just check that a given decomposition is optimal and valid. That's it. So it's very simple to define. And in AlgoTune, we gathered a bunch of experts, and we asked each expert to give us interesting functions from their domains. And so all in all, we have like 154 functions taken from the most widely used Python libraries. So you see a lot of NumPy, a lot of SciPy, things like CVXPy, which is an optimization library. There are differential equations. There's things in cryptography. We really went for things that we think many people use, and therefore it would be very interesting and worthwhile to optimize the runtime. Yeah. So in evaluation, I basically say, look, just do whatever you want to do. Okay, you can use the internet. That's no problem. You can, of course, look up the reference source code. So the function that you're going to be competing against, that's totally fine. You can use basically whatever Python package you want. We're going to see later, I have pre-installed like Cython and Numba. These are packages that allow you to write super quick Python code. Yeah, so you can use them and others. And you can also, of course, use the NumPy or SciPy or like any packages used in the original implementation. So if the original implementation used is like a NumPy function, you can, of course, use NumPy, feel free. So basically, this evaluation allows you to do anything. Yeah. And to basically see how good your model performs, we're going to generate example inputs using our generate inputs function. And these inputs will take the reference about 100 milliseconds to solve. And we then measure the speedup per task. And we aggregate these results into a harmonic mean. And then we get this one singular number, which is your AlgoTune score. So yeah, it's a harmonic mean of your speedups across all the tasks. And if you don't manage to speed up a function, that's okay. You get a speed up score of 1. So we don't punish you if you try but fail and like submit code that doesn't work, for example. You don't get punished. And yeah, so of course, to evaluate, we can't just give language models this task to do zero shot. We also built an agent, and the agent is pretty simple. So we have all the basic commands that one would need to write an agent that writes code. So you have your edit or delete. But in addition, we add in commands that are specific to algorithm design or runtime minimization. So for example, profile and profile lines allow the agent to basically take a piece of code and see how long it took each line to run for. So this allows you to see where the bottlenecks are, for example. And we, of course, allow the agent to evaluate its code on a training set of inputs or any input that it wishes to during training. So it's constantly getting feedback about, first of all, if its generated function is correct, but then secondly, if it has a speed up or not. So it's constantly getting feedback about that. Cool. And then just finally, we give you basically everything in the prompt. We give you, of course, an explanation of the commands, the task description, and we, of course, give you the reference code that you have to beat, and even the function that checks that your code is both optimal and valid, right? So we don't hide anything. We tell you do whatever you want to do. I think it's like one of the least limited or it's like the benchmark setting that limits you the least in terms of like agents. Cool. Oh yeah, the one limitation that we do have is that models get only $1 per task. So code optimization is something that you can theoretically do forever, right? It's not like a sweet bench task where you fix a bug and then that's it, you're done. And so we have to limit you in some way. And so we thought the fairest way was to give every model $1 and let them run, use up their budget and then stop them. And I think this is also a cool way to basically show the utility of cheaper models, right? Because otherwise, basically, the most expensive model is usually win in benchmarks. But if you have a cheap model that's also pretty smart, then it has a fighting chance to get a good ranking in AlgoTune, which I think is pretty cool. Cool. So let's quickly see AlgoTuner in action. So our agent in action. I chose to show this polynomial mixed task, which is basically finding the roots of a polynomial. And we see that among models tested, DeepSeek got a 4x, but O4 Mini got a 100x speedup, which is super interesting. So let's see what this model did. Okay, so it started out, it did an ls command that was badly formatted, but then it finally wrote some code that was well formatted, and it basically used a known iterative root finding algorithm, and it landed on a 72x speedup, which is very nice. Then it kind of tried optimizing its algorithm, but it was kind of failing. By the way, you see in the top, we always tell the model how much money it has spent so far and how much money it has remaining. So it's kind of like trying to optimize code, but it's failing these edits. It's not giving us code that compiles, and it keeps trying and it keeps failing. So then it decides, okay, I'm going to reset. I'm going to go back to the reference NumPy root finding function, and it gets a speed up of 1, as one would expect. And then at the very last turn, before it runs out of money, it submits this algorithm. It uses some, it's a JITted code that gets a 99.6x speedup. It's a different iterative algorithm that seems to work better. And so just to sum up what happened here, because I think it's kind of interesting, is it tried one iterative algorithm with 1,000 steps and got a 72x speedup. It failed a bunch. It went back to the reference and got a 1x speedup. And then it tried a second algorithm with 100 steps. So, 10 times fewer steps and got a 100x speedup. And the question is, why didn't it just try the first algorithm with 100 steps from the beginning? Surely that would have been better. And I think what I get from this is that models are very not consistent, and they behave somewhat like drunk geniuses. Like they do very smart things, but not in a way that you can say, okay, one thought leads to the next. They do things more in a way which makes you kind of like, what are you doing? You're just you're brute forcing this problem instead of thinking clearly. Okay, if this fails, then I'll go to this. And yeah, the train of thought here is very it's very confused. It's very random, and this we see in basically all models. So yeah, so just quick results. GPT 5.2 is the best, followed by Gemini 3.1, and GPT 5.4 is actually a bit worse than GPT 5.2 and Gemini. And Cloud 4.5 is good, but Cloud is very expensive, and as we know, Cloud the benchmark is limited by $1. And what happens often is when you give the models like the task, they kind of do this thing where they hallucinate an entire conversation with the system. So they're talking to each other. They're talking to themselves. And when Claude does this, it basically uses up a lot of its budget or all of its budget. So it doesn't get a second chance. So yeah, when you're expensive, it kind of plays against you, especially when you hallucinate things and waste your tokens. Yeah, so you can view the full results in AlgoTune.io. You can see for every agent and every task exactly what it did. It's all there, I think, pretty nicely. And yeah, we can go quickly if we have enough time. Let's see. Yeah, I think I have enough time. We can quickly go over the 3 categorizations of improvements that AlgoTuner achieved. So yeah, it sometimes I'll go over each one of these and what this means. Okay, so using a better implementation. So for example, we have this task. It's an optimization task called feedback controller, and the reference is a CVXPy implementation of this. And AlgoTuner with O4 Mini just changes the implementation to a scipy function, or to use a scipy function, and it gets an 81x speedup. Okay, so we didn't invent anything new. We just changed the implementation from one library to another. And actually, this sort of by looking at the packages used by AlgoTuner versus the reference, we can kind of we kind of understand which packages are good for writing fast code and which aren't. So if we see at the bottom of the table, CVXPy was used 27 times in reference functions, but only 9 times in generated function functions, like in LM generated functions. So a lot of the times the LM decided not to use it because it was too slow. So yeah, this is pretty cool. And of course, Numba is at the exact opposite. Numba is a library that lets you write super quick code, And so it was used a lot. Yeah, another just a cute little speed up is this SciPy function called correlate 2D. And our AlgoTuner with a bunch of language models noticed that correlation is just convolution with a flipped kernel. And this is mathematically equivalent. And if you just call this other SciPy function that does convolutions with a flipped kernel, then you get a speedup of 170x, which is pretty cool. Yeah, it's a very simple and mathematically correct way to do this. Cool. The other thing is rewriting or refactoring code. So if you can look at this example, on the left we have this multiplication of eigenvalues and eigenvectors, this matrix multiplication, and AlgoTuner with Opus 4 turns this into a scalar multiplication because we're basically multiplying eigenvalues, which are scalars, by the eigenvectors. And yeah, this leads to a nice speed up. Yeah, so just by noticing this little inefficiency, we can get a nice speed up. And of course, the very reliable way to speed up reference code is to use low-level code. So we talked about Python. This here is an example of number-JITted code. So this code, yeah, is especially like meant to run very quickly. And we see here that this SciPy Washington distance function can be sped up by a factor of 4 by just writing this nice JITted code. Which I don't know. I wouldn't necessarily expect that this widely used SciPy function would be so easy to improve, but apparently this is the case. And yeah, and there are many more examples on our website on a bunch of different tasks. So again, I'm just going to mention AlgoTune.io. You can look at a bunch of cool examples of models being, smarter than you'd expect them to, or maybe dumber than you expect them to. Depends on what your expectations are. And the one thing I want to say is that, again, just going back to this drunk genius behavior, we see that for every task, we have a different ranking of the models. So again, this points to inconsistency. Like models aren't, like they give you good results on one task, but then bad results on the next. We see many times, like for example, that GPT-5 is better than GPT 5.2, which is better than GPT 5.4. Like there's a lot of inconsistencies in the way the models solve this. I think this kind of diversity in the rankings means that there's a lot to be done here, and it's very interesting. How do we get models that are pretty smart to be consistent and to consistently give you good code instead of just hoping, like throwing everything at the wall and hoping that something sticks, which is the current behavior of models. And yeah, so we find many cool speedups, but not one of our models found a novel algorithm. So there's still a lot to be done here. And again, it doesn't feel like a scientist because it's a bit of a drunk genius. And yeah, I'll just wrap up here by saying that I made AlgoTune super easy to run. So you basically just need an AWS key and an open router key, and you can launch whatever model you want and whatever task you want very quickly. So here I'm just showing that I can launch AlgoTuner with Gemini 3 in like, I think less than 30 seconds. So yeah, I spent some time doing this, and if you just need an Amazon key and an open router key, and you're good to go. Nothing else. Yeah, and yeah, please visit our website algotune.io to see all the results for all the models across all tasks. I think it's displayed pretty nicely, and you can get a kick out of seeing some nice optimizations to maybe the functions that you use in NumPy or SciPy or some others. And yeah, I'm open to any questions while this rectangle packing task plays in the background. You'll see how AlgoTuner improved on this baseline approach. So yeah, thanks.
Awesome. Thanks, Ori, for the great talk. So we have questions coming up here in the chat. So maybe let me first read one here from Robert. So is there a hardware constraint or default for this? And do you fix the library versions to keep the benchmark stationary?
Is there a hardware constraint? Sorry, I missed this.
Yeah, is there any hardware constraint or default, like for the hardware to run
Yes, I
on this
mean,
benchmark?
it's yes. I mean, now whether we have it on AWS. I forgot what instance, but it's. I mean, everything has to run on the same hardware. I don't mind if you would like use your own hardware as long as the baselines, like the reference functions and the generating functions, run on the exact same hardware. And it should be able. You can configure it to your hardware, but I think that the standard thing should be just using Amazon's cluster.
I see. And do you fix the library versions to keep the benchmark stationary?
Yes, we do. We do fix the variables. Yeah.
Okay. And maybe there's a quick question here, and because I saw also some asking the same questions. So how do you avoid reward hacking across so many diverse tasks here?
Yeah. It's just a challenge. I mean, we just launched a bunch of models. Like right now, I'm pretty confident. So we have these is solution functions, and these functions check that a solution is both valid and optimal. And I mean, going through the iterations, I think we've already ran 15 plus models, like on each task. And so every time we found some, crazy speed up, like a 1000x, we knew there was some reward hacking going on. And so we've iteratively like made those functions better. So yeah, when you run AlgoTune, you should not, if there are any results that are like really high, like 1000x, then you should probably look at if there's reward hacking going on. But
Mhm.
yeah, I want to say that after 15 iterations or even more, like we think that there's relatively low amount of reward hacking currently left.
Mhm. I see. Makes sense. I think we can take one last question here. So there's a question from Sam. So when you're running the test, how do you ensure that the version of the LLM that you serve is consistent?
The version of the LLM, I mean, I guess versions change over time. And I mean, for the past
Mhm.
couple of LLMs, we've just, like the week it came out, we just ran it. We do everything through open router. Um,
Mhm.
yeah, things could change, I guess, but we only measure it basically when the LLM comes out. Um, and I guess not too much over time.
I see. Okay. Yeah, perhaps unfortunately due to time limit, we don't have more time to ask more questions, but keep the conversation going in the chat. And after this, we will let's thank Ori for the talk. And we will have a short break after this. So perhaps I'll hand it over to Dan to give some updates on the